they're talking for me. So I would like to welcome the first speaker, who is David Root from Canada. David, you are there, right? I can see you. Yes. So David is, well, he's from Australia, and he has a PhD in aeronautics, and that was taken in London at Imperial College. He worked in different universities and at NASA as well, and he published a book called Small Wind Turbines. He is or was, that you need to tell us, director of Wind Energy Institute in Canada. As far as I understood, now you are retired, but I don't know if you are still involved in those activities. And his presentation will be on the modeling of the yaw response for tail fins for small wind turbines. So we start, Al, and that's good because we are fresh, then we can get the most out of it. David, are you there? Can you share your screen? Oh, yes.
Can you hear me now?
Yes. We'll just put the volume a little higher, but it's good.
Okay,
So,
or I can put it a little.
See if it goes well.
I'll put it a little bit higher on my machine as well.
We lower it. We put it higher here. Now it's good.
Okay. Okay. So I've got till about 6:30. How do you want 6:30 my time? It's in the evening in Australia. How do you want me to do this? Do we take questions as we go through, or do we wait for them at the end?
In principle, we could wait at the end, but that's your call. It's your presentation. Whatever you prefer.
I don't particularly mind. I just need to get my screen a little bit smaller so I can find the icons at the bottom of it to get it into go. Always the Zoom icons are in the way.
Here in presence, if you have a question, please speak loud because we tried the microphone. We can get up to down,
okay,
but you need to speak loud. Okay.
Okay. So is this coming up in the correct mode? The presentation mode?
Yeah, we can see.
Okay, great. Well, thank you very much for the opportunity to speak to you today, your time, and tonight, my time. I'm still officially associated with the University of Calgary, but I have retired and returned to Australia where I come from. So that explains the different continents between my physical presence and my affiliation. So I'm going to talk to you about the work that we've been doing over the past few years on modeling the yaw response of tail fins for small wind turbines. There's my email address. That is still my current email address. So if anybody has any follow-up questions, please feel free to ask them. I have to go through fairly quickly the material that I have to present because of obviously the time constraints. And I want to point out right at the beginning that this is a multinational project that we're involved with. This is focused on the developments at NREL that I will tell you about in the next slide, I think it is. Oops, that's the next slide. I was looking for my pointer options. Pointer options, so laser pointer. Okay, so the work has been divided between myself and Mohammed Hammam. We're responsible for the model that I will tell you about. Then our colleagues in Italy that have a nice big wind tunnel that's very suitable for doing the experiments on basic tail fin behavior that we need. They're involved as well. And of course, being an NREL project, there's several people from NREL that are involved with it. And I need to emphasize that this is very much a team project. I've put my name on the front of the presentation because I'm presenting it, but there's lots of contributions from everybody else. Okay, so a little bit of background that small wind turbines, small horizontal axis turbines that are less than about 20 kilowatts, and that's a rough figure, of course, often use a tail fin for yaw alignment. The yaw alignment is very important because it influences the power output, and something that not a lot of people seem to appreciate, has a big impact on the gyroscopic loads that are felt by the blades and the main shaft, and then are transferred onto the tower. Also too, and this has been a big component of our modelling exercise, the tail fin is essential for the turbine starting at low wind speed, because the yaw angle, and I'll use the symbol gamma for the yaw angle, is often high. And also too, bearing friction in the yaw bearings may be important. And if we add on to that the fact that many tail fins have a high aspect ratio, then that shows the need for a nonlinear model. So what we've done is taken the linear yaw behavior model that is based on unsteady slender body theory, and this is the same model that people that design wind vanes for wind direction measurements use. And we have extended it. And what we're doing is providing a module for OpenFast. When we started this project, OpenFast had a very simple model for the yaw behavior, and we're trying to improve that as part of what's called the DWAM project that is indicated in the reference at the bottom of the page. So what we're intending to do is extend the theory of the yaw behavior of a tail fin to include a large range of gamma, high aspect ratio, and bearing friction, provide a tail fin model for incorporation into OpenFast, and that has actually been done. To give you a little bit of the history, I'm going to start with the first work that we did, which was based on generic shapes of tail fins, such as delta wings, ellipses, and rectangles. And we developed the theory by comparing it to the wind tunnel tests that I'm going to explain later on in the presentation. These were of generic tail fin shapes without a nacelle or rotor attached to the tail fin. The fins were yawed to large angles, 40 degrees and 80 degrees. Don't worry about the minus sign. That's just for consistency with the experiments. They were released from that angle and their motion is recorded. And I'm going to finish up the presentation by telling you briefly about a much more complex planform from a commercial small wind turbine. So here's our nonlinear equation. I just don't have time to go through any of the derivation of that equation at all. Gamma is the yaw angle, dot denotes differentiation with respect to time. IZ is a moment of inertia. The other parameters you'll probably be able to understand at least a little bit about it. The coefficients K subscript P, K subscript V, and C subscript DC are the basic components of the model. So KP is what's called the potential flow coefficient, and it is a term that becomes linearizable at low values of gamma. K subscript V is the vortex flow coefficient, which models the nonlinear vortex forces that you get at high angles of attack. And CDC is the high angle drag coefficient, which is also a nonlinear term. And importantly, the X1, X2, and X3, they're called separation functions. This is the convention that's grown up over time from delta wing studies. They basically control the relative importance of the coefficients Kp, Kv, and CDC. And the separation functions themselves give each of them has two further parameters. And so what we have is a situation where in this equation here, we have three parameters here, which are known for many generic planforms, and that's why we started with delta wings, ellipses, and rectangles. The separation functions are less well known. And if we take into account that the separation functions each have two additional parameters, we're getting up towards a large number of model constants. And so we might get overfitting if we try and fit the model to the data. And here's a very famous quotation that I rather like from John van Neumann: give me 4 free parameters and I can fit an elephant. And if you give me another one, I'll make his trunk wiggle. So one of the problems that you have when you have a model with a large number of adjustable parameters is that you might get local optimizations in the fitting, and etc. So what we've done is to keep KP, KV, and CDC constant and use system identification to find the 6 constants for X1, X2, and X3. And then if we add in the frictional torque, and here's our friction model here, we get another 4 constants. So life gets pretty complex. So here we go to the wind tunnel, and here you can see a rectangular tail fin here and a delta tail fin here in the wind tunnel at the University of Perugia, yawed to an angle, released, and the subsequent, what looks like a damp linear response was measured. So what we did was to do tests at 17 meters per second, a wind speed that's high enough that the friction is negligible. Then we dropped the wind speed to 5 meters per second to determine the friction constants. And then we thought, okay, we'll go somewhere in between, and hopefully we'll be able to validate the model with those results. I've put the table of the model constants here. The measure of the fit, I won't explain how this percentage is achieved, but all you need to know is if the fit is 100%, it's a perfect fit. And you can see that we get pretty good fit for our model. And here's some typical results. Here's the rectangular tail fin at 17 meters per second with no friction. You can probably just see the blue line, which is the measurements. The red dash line is the response, the model response with the initial constants, and the black line is the optimized constants. And you can see that we can get pretty good fit if we can optimize the constants. If we go down to 5 meters per second and add friction, then basically friction knocks off the peaks in the subsequent maximum values of gamma, which is exactly what you would expect because friction is a damping-like term, and we get very good agreement there as well. So with that, and we managed to do that for all the generic tail fins, and when we tried it at 10 meters per second, we got slightly worse fit on average, but still pretty good. Unfortunately, the data at 10 meters per second was not sensitive enough to test the friction model because the wind speed was still too high and the aerodynamic moments were significantly greater than the frictional moments. So we started off with the generic planforms of delta wings, rectangles, and ellipse, and we have a model that works well for them. The question that we wanted to ask, or that we then asked, is, okay, that's fine for very simple tail fin shapes, but for some strange reason, the people that make small wind turbines often use a very, very much more complicated tail fin shapes. And here is a model of the tail fin of the Pika T710 small wind turbine. It's a 1.7 kilowatt wind turbine. And here is a situation where we have very little ways of guessing or estimating what the model constants are. So what we have to do there is to fit virtually all the constants to the model. And here's an example of how we do that. You can see again, the black or the blue is the experiments. The red dash is the initial parameters, our first guess for the model constants. And then we get the blue, which is the optimized values. And you can see we're able to get just from the wind tunnel testing and using system identification on those results, that we can get a very good description of a realistic but complex tail fin landform. And so this is the procedure that we would advise people in the future to, if they want to use OpenFast for their small wind turbine modeling. Doing these wind tunnel tests is pretty straightforward. And if you use system identification to get accurate values of the model constants, then you'll have a pretty good model from us. However, there's still quite a bit to do, because everything that we've done to date has been based on wind tunnel tests, and the real world out there is a little bit more complicated than what we can reproduce in a wind tunnel. So one of the reasons that we used the Pika T710 was that it's actually been erected on the NREL test site, and its field test behavior will be measured, and we'll get some real data on the tail fin performance. And here's some of the things that we will be looking for. We'll be focusing on the low wind speed performance, because a small wind turbine needs a tail fin to get started. We'll be looking at the effect of the airflow through the blades on the tail fin, because nothing in the model that I've showed you so far gives us any information on that. Then, of course, we all know that real wind turbines have a yaw error, and so we'll be looking at that and trying to track down some of the reasons for its causes. And particularly for our understanding of the loads that these small wind turbines experience, how does the yaw behavior interact with the RPM of the blades to generate those gyroscopic loads on the blades and the main shaft and the tower? And the other thing that we're going to be doing is looking at the effect of varying wind speed, because I didn't show it in the model because the equation is complicated enough, but there are extra terms that you have to put into the model if you want to model the effect of varying wind speed. We tried to do this in the wind tunnel. The wind tunnel in Perugia can vary its wind speed, but the time scale over which it can vary is not small enough to really test our model. So we want to do that as well. As I said, if anyone wants a copy of this presentation, just send me an email and I'll send it to you. Here are some of the references that we're starting to accumulate on this work. And with that, Danielle, I have finished.
You need to clap again because we were muted. Sorry. Thank you very much, David. So just you mentioned Perugia University. We'll have a speaker at the university tomorrow as a first speaker at 1, unless there are changes. So I don't know if
yes,
you know, but
yes, he was heavily involved with the testing that I just described.
Perfect. And then, yeah, the presentation, if it's okay to share it with everyone, you can just send it to me and I put it in the conference proceeding.
I shall do that, yes.
Together with also, if you have any link to the articles, or if it's something open access, whatever you want to share, you just send it to me and I put it on the page. Okay?
Yep, so shall do. Thank you.
So we'll have now some questions. For the ones online, please raise the hand. You can do it under React, and then oh, it should be, yeah, React, and then you have raise hand, and then when I give you the floor, then please unmute yourself and put the camera on so that we can see you as well. We have a question here from the audience.
Yes, hi David, it's Robert.
Hey, how are you?
Yeah, thanks for a very nice presentation on the tail fin. So I was looking at your curves, and the overshoot you have is around 30 degrees or so for the cases you have here. Can that be kind of controlled or diminished, or is it an issue?
Yes, that's something that we've thought a fair bit about, but you have to remember that these are ideal test because it's basically a step function in yaw angle. So in reality, it's unlikely that you would get such an extreme wind direction change, and the IEC standards on wind direction change also suggest that that's unlikely. So in reality, when you get less than a step change in the wind direction, you're unlikely to have that level of overshoot. But it's more or less mandated because I deliberately didn't talk about the response in terms of linear second order systems because I wanted to emphasize the nonlinearity of the response. But if you qualitatively, it's still similar to a linear second order system. And with tail fin design, it's extremely difficult to get a damping ratio greater than about 0.3 for a tail fin. So you're bound to get an overshoot, and probably a significant overshoot with whatever tail fin geometry you use.
Thank you, David.
Thanks. Is there any more questions? Yeah.
Just another question, Domenico from Investor Relations. I noticed that there is also an out of phase when you use the friction. Is that, you know why? It's not only reducing the amplitude, but also some out of phase of the peak.
I'm sorry, I didn't get the question clearly. Danielle, would you be able to repeat the question?
Just get the microphone a little closer.
When you show the introduction of friction in your
Yes.
I noticed that there is also an out of phase of a peak, not only reduction of
Yes.
Do you know
Yes. No. I think we have a reasonably good friction model, but the problem is that it's not a good situation to look at bearing friction, because most of the bearing friction models are designed for relatively high RPM. Okay, whereas the maximum yaw rate that you get on a small wind turbine, as mandated by the IEC standards, is about 30 RPM. That's a really low speed for a bearing. So it means that the bearing is going to operate somewhere between the static and dynamic range. It's in what's called the Strybeck range. And you can look at the tribology of the lubrication to get a better idea of that. But it is actually a very complicated region, and it might even depend, the frictional behavior might even depend on whether the bearing is cold or warm. So if a wind turbine has been sitting still for a period of time and the wind starts to blow and it needs to yaw into the wind direction, that the frictional resistance in the yaw bearing may be different to if the turbine's been producing power for several hours. So all that means that the actual frictional behavior is likely to be very complicated. On the other hand, we're trying to get information about the friction in the context of a model that already has a large number of adjustable constants. And what we found, I should have made it a bit clearer, but when I put up the friction equation with 4 model constants, we just found that we were overfitting the data. There's just too many constants to vary for each particular situation that we weren't getting consistent values of the constants. So that's a very long-winded way of saying that we really can't say anything other than a constant frictional torque is not a bad approximation to the bearing friction. And so questions about phase differences and whatever, I think, are a little bit too deep for us to get into at the moment. Maybe we'll see something different when we start analysing the field tests, which I hope will happen very soon. But at the moment, that's, I think, the best response that we can have.
Yeah. One more question here.
Yeah, hi, David, it's Robert again.
Hi.
Yeah, the nice model you developed here, would that also be applicable for furling analysis if you had a turbine with this in some?
I have a constitutional aversion to furling, Robert. I try and avoid it under all circumstances, and partly for the reason that it's extremely complicated a process, and I don't think anybody really understands it. And I also think that, generally speaking, the small wind turbine industry is moving away from furling with the advent of electrodynamic braking, basically the shorting of the output of a permanent magnet generator as the main overspeed protection. So I've never felt it worthwhile to spend, a considerable amount of my intellectual effort in understanding what furling is. So I can't really give an answer to that.
Thank you.
Okay. Any more questions? We have time for, well, we don't have time for more, apparently. So thank you very much, David. I
Thank
don't know
you.
if you will stay with us a little longer. If not,
I will stay for a
will
little
be
while. Yeah.
available.